Chapter 3, Motion in Two Dimensions. So whenever we measure anything in physics, whatever the quantity is we're measuring, whether it's length, area, volume, mass, density, whatever, certain things we only think about magnitude. So in layman's terms, what does magnitude mean? In layman's terms, it's just a number in a unit. So if I ask you, like, how long does it take you to drive to school? And you say it takes 15 minutes. Time doesn't have a direction. So there's a lot of things that don't have direction, so they're just a number in a unit. So here are some examples. Again, mass, time, age. So the word magnitude just means the amount, how much of something being measured. So it's a number in a unit, so example, 20 meters. So scalar quantities have magnitude only. So a scalar quantity is something that just has a number in a unit. So distance, speed, mass, temperature, time. And then here's examples. A vector quantity has both magnitude and direction. So again, some things have to have a direction associated with it. So the direct ones that are similar yet different: distance, displacement, speed, velocity. Force has to have a direction. Acceleration has to have a direction. So some of this is a review from the last chapter, but I want to make sure you understand it, because in this chapter we're going to start talking about things that are going in two dimensions. So that's why the direction is extremely important. Now, how do I represent a direction? Well, we can do it by a geographical direction, like north, south, east, west, or sometimes I can just draw an arrow saying it's going to the right. Or I can have it from a frame of reference. So you know how in math class when we graph and we say up and to the right is positive? Well, maybe I want to explain, normally in math class you express the angle counterclockwise from the positive x-axis, okay? And not in this class. When we take college physics, you're going to do rotational motion, which is torque. And when you do torque, again, you have to have a sign convention. So the sign convention is counterclockwise is positive and clockwise is negative. So sign conventions and all these things are important. Now, in math class, if I was going to add two numbers, so if things are scalar and they don't have a direction, and I say 2 plus 3 is 5, okay? But what now if I had 2 and I want to add it to 3, is my answer 5? No. Only if these are going in the same direction, 2 plus 3, would it be equal to 5. But when they're going in different directions, I cannot add them algebraically. I have to add them vectorially. Okay? So when I add things algebraically, I get called a sum. When I add things vectorially, and that's how I would add vectors, I get something called a resultant. So the resultant is single vectors that have the same effect as two or more concurrent. So what does the word concurrent mean? Concurrent means two vectors acting at the same point at the same time. So let's say somebody was flying an airplane, and let's say the airplane was, that's not a great picture, but let's say the airplane was flying north, but then there was a wind blowing west. The airplane might actually go in this direction, okay, or a boat or something like that. So concurrent just means acting at the same point at the same time. So the resultant of two vectors can be found either graphically, doing it to scale, that means using a ruler, or we can do it mathematically. So we're going to today look at doing it mathematically. So a vector is represented by an arrow drawn to a scale. Now it's important to understand the parts of the arrow, as simple as that might sound. So this part is called the head, and this part is the tail. Why does it matter to know the parts of an arrow? Because the one rule for adding vectors is that we add vectors head to tail. Okay? Now this just shows a little diagram. So if I was going to add them to scale, and this was 8, and this was 6, because they're going in the same direction, I add them head to tail. So from the head of this vector, I put the tail of the other, and then the resultant is from where I start to where I end up, and then I can measure that if I was doing it to scale. This shows you if they're going in opposite directions. This is where I start. I draw my 8 kilometers. From the head of this vector, I do the tail of the other, and the resultant is from where I start to where I end up. Now, when they're going like this, and it's on the same plane, like it's x and negative x, it's really easy because you would just call this positive and you would call this negative, and it would be easy mathematically. What we're going to do in this chapter is we're going to do ones that go in two directions, okay? So let's say I had one vector here, this one was 10, and this one was 5. To find the resultant is from where I start to where I end up. These have to be added head to tail, and then I would measure this. Now, we can all do this mathematically, because when we look at this, this is easy. This is a right triangle. If I wanted to find the leg of this right triangle, the hypotenuse, I would just use the Pythagorean theorem. But the thing about a vector is, this is not the only answer. Because I can use the Pythagorean theorem to find how long this is, but all vectors have magnitude and direction. So what I need to do is I need to find that angle in the triangle. Well, if I look at my picture, if I want to find this angle and I know opposite and I know adjacent, I know that tangent theta is equal to opposite over adjacent. Okay? And that's how I would do that. All right, so what is the one rule for adding vectors? Vectors are added head to tail. So it says draw one vector to scale. So let's pretend I had the two vectors like I showed you, 2 plus 3. If I had 2 like this and I had 3 like this and I wanted to add them together, what I would do is here's the 2 and then I add the 3, and then my resultant would be like this. But we're going to start off doing easier ones, so we're going to start off with something more like this, 2 and 3. So we have right triangles. So if I added those together, I draw my 2. From the head of this vector, I do the tail of the other, 3. And then from where I start to where I end up, I draw a line. Now, how do I know where to do the head and the tail? The start is always going to be the tail, and where I end up is always going to be the head. Now, what if I didn't add them that way? What if I started off with the 3 like this, and from the head of this vector, I did the tail of the other like this too? From where I start to where I end up, does my resultant look the same? It's the same size. Is it going in the same direction? It is. The only thing I have to be careful with, if I solve, how do I measure the angle? You always measure it from the tail. So it's easier to measure the tail inside, but what you notice is that these angles aren't the same. Now this is the same. These are supplementary angles. So we just have to be careful. Are we expressing the angle from here or from here? Okay. So again, let's go over the rules. They're pretty simple. So draw one vector to scale, put the tail of the second at the head of the first. The resultant is now found by joining the tail of the first to the head of the second. The length is measured, and you can do it by scale, and then the direction you could use a protractor, but we're going to do it mathematically because we all know Pythagorean theorem and definition of sine, cosine, tangent. Now, next class, what we're going to do is, this shows how to add 3 vectors graphically. But what if I want to add 3 vectors mathematically? Okay, that's what we're going to do next time. All right, so what are some things that we need to review? We need to know that every triangle has 180 degrees. If we have a right triangle, it has a 90-degree angle, which is opposite the longest side, which we call the hypotenuse. We use the variable theta to represent an unknown angle. Sometimes we use another one called alpha. Alpha you might use after you use theta. Now, do we have to have memorized the definitions of sine, cosine, and tangent and Pythagorean theorem? Of course we do. That's math that you need to know to be successful in physics. So sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent's opposite over adjacent. And the Pythagorean theorem says c squared is equal to a squared plus b squared. Now, let's say, here's one example. So let's say the engine of an airplane pulls it north at a distance of 600 meters, while at the same time the wind pushes the airplane 200 meters east. Find the resultant. Now, I just showed you how to do it graphically. So what I did was I actually did this. I drew this. I took this ruler and I drew this. See how I drew it to be 6? See the 6? This is 6 centimeters. So my scale was at 100 meters is a centimeter. So this represented the 600 north. And you see how I drew it up because north is up. From the head of this vector, I drew the tail of the other, which is 200. From where I start to where I end up, I drew a line, and that was my resultant. Then I actually took the ruler, and you measure it, and you say, oh, this is like, 6.2 or 6.3, which would be like 630 meters. Then, to measure this angle, you use a protractor. Now, mathematically, it's a right triangle, so it's easy to do. So if I want to do the same thing mathematically, I just notice here this isn't a scale. I just do it freehand because when I draw a picture freehand, it helps me to conceptualize it. So I drew my picture, and then from where I start to where I end up, I drew my line. That's my resultant. I used the Pythagorean theorem to solve for it, and then the angle, you always measure from the tail of the resultant. And what I did was, I knew opposite and I knew adjacent, so I used tangent to solve for that. Okay, so the math that we're doing is math that everybody in this class already learned before. It's nothing new, but we're reviewing the math. And this is going to help us to do two-dimensional motion in physics because we're going to do projectiles. Then, for part B of the homework, we're going to look at resolving vectors into components. So what I just showed you how to do is, let's say I have this, and I add them head to tail, and I get a resultant. So vector resolution is going to help us when we have to break something up into components, or when we want to add 3 or 4 vectors. So what we're going to practice B is the opposite. Instead of having this and this add up to R, we're going to have R, and we're going to say what 2 vectors, when added together perpendicularly, one's going to be horizontal and one's going to be vertical, are equivalent to that same one. So we're just going to do the opposite for part B. And that's called vector resolution. So vector resolution says I have a single vector, but now I want to say what are the 2 vectors that when added head to tail, a horizontal and vertical, are equivalent to it. So the 2 components, we're going to have a horizontal and we're going to have a vertical. So for example, for this one, this is my vector V, and then I'm going to say, well, what adds up? What are the 2 horizontal and vertical components? So when I have my vector, let's say this is my vector V, how do I know how to begin? I go here to the tail, my starting point, and I go horizontally until I get to the point where the vertical component head to tail is going to be a right angle, and it's going to go like that. So that's how I know where to stop. So I start here, I go horizontal. When I get to this point, I go vertical. And how do I know which way the arrows go? Because it's like this is the start of a path, and this is the end, and I want these to point in that direction to get to that point. So which direction these arrows go in, it's very important. Why is it important? Well, let's say my vector went like this. The components then are going to go like this and like this. So you see how this one goes down and that one goes to the left? So according to our standard sign convention, these would be negative. Okay? So how do we do it? So we start off, here's an example. It says find the horizontal and vertical components of the following vector. So here's my vector. Its magnitude is 50 newtons, and then it's acting at 30 degrees. So what you do is you draw your vector, and really on that same diagram, this is where I start. I go like this, and then this is going to be the x component. From the head of this vector, I do the tail of the other, and that's going to be the y. Now, if I have a right triangle, and I know the hypotenuse, and I know this angle, can I find the other two sides? Of course I can. And that's all we're going to do for practice B. That's how easy it is. How do I know to use sine, cosine, or tangent? So this is what you do. You just write them down. So sine of theta is opposite over hypotenuse. So when I look at my picture, if this is my angle, that's opposite, and that's the hypotenuse. So sine of theta is v sub y over 50. So v sub y is 50 times the sine of 30. And then you can figure that out on your calculator. Now let me show you. These are the calculators we're going to be using in class. So this is the way that you would press it. Everybody look up and look at the buttons that we're going to be pressing. So I'm going to press first 30, then sine, and then I'm going to press times 50 equal. So that comes out to be 25. Then this one, I'm going to press 30 cosine times 50 equals, and that comes out to be 43.3. So that's how we use this calculator, and we'll practice using these.